So the value of z is negative 1398, and the value of x plus h is 15.0001, and the value of y is just 15. So when I compute f of x plus h comma y, it's going to be a small change with respect to the original value of x plus y. So now it's negative 1398.0017, and that's going to help me. Is going to help me to compute the derivative of or the partial derivative with respect to x. Again, I do a similar procedure, but now I compute the f of x comma y plus h, and again this small change, and that helps me to compute the partial derivative with respect to y, and I do so by following the formulas, the formula that I just described here, and we can obtain a partial derivative of with respect to both x and y. And then we can compute the normalized gradient in the x direction, and we can compute the normalized gradient in the y direction. Well, by normalize, it means the following: the derivative as it is right now is showing 117 and 82 negative, but a vector of that magnitude would be probably too long. So what we do is we normalize this vector to have a norm of 1. That's the length of the vector is 1, and all we do is we apply our knowledge about vectors, which is dividing the length in the component x by the norm of the vector, and that gives us a normalized gx with negative 0.8189 for x and normalized g of negative 0.5739 for y. And then we start with the step of 1, and we need to control the step in order to achieve the desired accuracy. I'm going to explain more about that in a moment. Then we identify the steepest ascent step that we're going to take, and that is depending on the step of this that we're taking, the normalized step. In this case, the vector is going to be a size 1, and that means that we just multiply the step times this normalized component of x, and we just have the same value. And then 1, which is the normal value of the step, times this normalized value for y, and my y in this case repeats for this first instance. And we check the signs of the gradient. And the signs of the gradient right now are both negative in the x component and negative in the y component. We're going to use that later on. So once we have these components of the steepest ascent, we're going to use these as the values that we're going to add or subtract to the current points. Remember, we were originally in 15, 15 to evaluate this function. So now, after we take into consideration that we are going in both the negative direction in x and y, by those values obtained as a step size, those are the estimated values that reduce, not reduce, but actually increase the value of the objective function as the fastest possible rate. And then we take that step and we repeat the whole process. We have computed the value of z. We compute f of x plus h and y. Again, that depends on the value of my h, which is supposed to be small, or it has to be small, and y doesn't change. I compute f of x plus h comma y, and I also compute f of x comma y plus h, and with those two vectors, again, I can compute the gradient, which is these two columns here, or partial derivative of z with respect to x and partial derivative of z with respect to y. And again, you see the vectors are changing a little bit, and the normalized vector is similar, but it is not exactly the same number, of course. And now we have decided to increase the step. Why? How do I arrive to the conclusion that I should increase the step? Well, what I do is I check the sign of the gradient, and the sign of the gradient is negative and negative again. So if the size of the gradient is negative and negative, in general terms, we are heading in the same direction, sort of, what the previous step, and that means that if both these cells with respect to the previous is the same sign as the previous component of the gradient, both for x and y, then I am going to write here 1 in case they both are the same, implying that in general is going in the same direction. And if they're going in the same direction, I'm going to take the decision to increase my step size by 10%. And then the steepest ascent components are the vectors that I originally had, now multiplied times 1.1. So the normal of this step is now 1. The norm of this step is now 1.1, and we go now in that direction. The reason for doing that is if we're going the right direction, well, why not take a faster path or larger steps? So if we take the larger steps, we should get faster to the region of interest for us. So we keep repeating this process of computing the gradient at every next point, and you see if we're heading the right direction, in this case decreasing both x and y, the steps start to increase by a factor of 10%, and we keep doing that a few times until we finally identify that we went from a negative sign in the step to a positive 1 plus 1. That means basically the gradient is suggesting to go in the opposite direction. And since we were coming from there, it means that we exceeded the point from where we should be going to. So what we do is whatever the step we had before, in this case the previous step was at 2.85. Now the step, if there was any change in the signs, and we identify that there was a change because this number is 0, the question when it's satisfied the condition for it to identify that it's different, I place a tag or a flag of that being equal to 0. When that's equal to 0, we are going to use a step size of just 10% of the previous step. And that is, we need to go back in the same direction, but the step should be smaller, because going in the previous direction with the larger step is only going to take us back to our original position, making no further improvement. That means that every time that we change the direction, we are getting closer and closer to a region of interest to us, in which we now need to take a magnifying glass. Imagine a magnifying glass in which now we need to search more carefully for the point that we're looking for, and that's why we use 10% of the step. And now we are going in the direction again of the gradient, of course, but with a smaller step. And then from that particular position, it suggests, you're going in the right direction. So now again it starts to increase the step until again we find that, okay, that last step might be too long. You need to go back exactly where you were coming from in general, from a plus situation to a negative situation. And again, you see the step size is reducing, again using a larger or more powerful magnifying glass, and this process keeps going until we achieved a very high resolution, because now the step size or the step sizes are in the order of the power of -6. That's 1/1 millionth. And at that particular point, for practical purposes, we have achieved the maximum that we are interested in. Compare this value here to the value that we have obtained in the past. So we can take that value from the end of our computations. Take that value and paste it maybe here. And we might still have an error, but the error is pretty much negligible. And we have achieved, without knowing which direction to go, originally just with 1 point and computing derivatives, we have obtained the maximum point. And many programs, implementation of in programs, commercial programs, use this algorithm. Of course, they don't keep all these solutions. They keep only the latest computations. Thank you.